We are always told that lemon is acidic while soap is basic. Simply put, it has always been regarded that the higher something is on the pH meter, the more alkaline it is, and the lower its pH, the more acidic it is. However, have you ever wondered how are we measuring all this? From juices to fruits and to various commercial products. The answer is through a pH meter. A pH meter is an instrument used to measure hydrogen ion activity in solutions. In other words, this instrument measures the acidity or alkalinity of a solution. The degree of hydrogen ion activity is ultimately expressed as the pH level, which generally ranges from 1 to 14. You'd ask, how does it work, right? First, we must deem that a pH meter is comprised of 3 parts: a pH probe, a reference pH electrode, and a pH meter itself. It is the electrodes inside a pH probe that measures the pH of the solution. The pH probe is connected to the pH meter display panel to show the measured pH value. In current pH meters, combination electrodes have the glass hydrogen ion sensitive electrode and an additional reference electrode all in one housing. As the electrode is immersed in the test solution, the glass bulb senses the hydrogen ions as a millivolts due to the positive charge of the hydrogen ions. The electrolyte or internal solution picks up the millivolt signal from the glass bulb. That signal is then passed to the internal electrode. The AgAgCl wire then passes that signal to the electrode cable that leads to the meter. Now that we have learned all about it, we should start doing some experimental sample. Let's say that we have to do a potentiometric titration of an unknown weak monoprotic acid. In this virtual experiment, we are to generate a titration curve and identify equivalence points using the graphical method. Hypothetically, we have already prepared and standardized our NaOH solution, and our laboratory assistants have already given us our unknown acid. It is then time for us to prepare our pH meter and our titration setup. Before we begin in the approximation of the equivalence point, we must first calibrate our pH meter with buffer solutions of pH 4, 7, and 9. Why is this important? Due to the sensitivity of pH measurements and the ever-changing characteristics of each substance tested, calibration of a pH meter is extremely necessary and beneficial. Calibration of this instrument should be performed regularly to ensure over-accuracy and reliability of the device. To calibrate it, we need the buffer solutions, a beaker for our washings, a wash bottle, and tissue papers. We need to wash the end of the probe and wipe it with a lint-free tissue paper. After doing so, we can dip it in the pH 7 buffer. Remember to always calibrate with pH 7 first. Once done, press the calibrate button, and when the meter accepts the value, it is time to wash again the end of the probe and wipe it with tissue. The same procedure can be done for buffers pH 4 and 9. Now that we are assured that our pH meter is now calibrated, we can then pipette a 100 ml aliquot portion of the unknown into a 400 ml beaker and place a magnetic bar. Now, we place the beaker on top of a magnetic stirrer. Afterwards, we turn on the stirrer and set up a burette directly above the beaker filled with the standardized NaOH solution. We need to remember to measure and record the pH of the solution prior to the addition of the NaOH by dipping the electrode at about 1/2 inch below the surface of the solution. And by the way, make sure to rinse the electrode with distilled water after each measurement. In this case, we are now to titrate the unknown by adding 5 ml of NaOH at a time. We also measure and record the pH of the solution after each addition. We repeat this 5 ml addition until a total of 30 ml volume was added. And when the volume range in which the sudden change in pH occurs, the equivalence point is within this range. This is so tedious to watch. Well, why don't we just fast forward? From our recorded data, we found out that this is the titration curve of our unknown acid. Now that we have generated this curve, how can we know what our unknown acid is? Well, that's quite simple actually. We just need to find the half equivalence point because the pH at the half equivalence point is equal to the pKa of the acid. It seems that we approximately have a pH of 4.8 in the half equivalence point. Let's research then what acid has this pKa. Found it! According to literature, acetic acid has a pKa of 4.8. Henceforth, our unknown is acetic acid. Good job! We all learned about pH meters and potentiometric titrations today. And through simple ways, it can easily be denoted how useful these tools are in determining and characterizing samples. To think that this is only in a small laboratory scale, what do you think are its potential in the big processing industries? To name a few, it is used in clinical chemistry for the analysis of metals, for the analysis of cyanide, ammonia, and the like in water or wastewater, in agriculture for the detection of different elements in soils and fertilizers, in detergent manufacturing, food processing, cosmetic production, and a lot more. With this, we can know that pH meters and potentiometric titrations do not only stay in laboratories, because they are one of the backbones to why so many products and processes are paved way. So, the next time you ever think about how acidic or basic something is, remember that you can always get up, put on that lab coat, and use what you've learned to discover more in the vast world of chemistry.